This is Geometry Lesson 9.3, talking about special right triangles and simplifying radicals using those special right triangles. Today we're going to talk about right isosceles triangles. So as you can see in the picture here, we have multiple right angles in the triangles, and then we have two sides the same length, so that means they are isosceles. And when we're trying to find the hypotenuse, we will be doing the Pythagorean theorem. So for this first example, my legs would be my A and my B, and I'm looking for side C. So A squared plus B squared equals C squared. 1 squared is 1. 1 plus 1 is 2. And then when I'm trying to figure out what C is, I need to do the opposite of squared, which is the square root. So C equals the square root of 2. Now I could create a decimal answer, but that would be an ugly number. So at this part, we are just going to leave it as the square root of 2 since the radical of 2 cannot be simplified. Okay, now if I repeat this with the second triangle, we will see a pattern. So again, A squared plus B squared equals C squared. And again, we will apply the square root to get rid of the squared on the C. But square root of 8, again, not a perfect square, so it won't come out very nice, but it can be simplified. So I'm going to break down the square root of 8 as the square root of 4 times the square root of 2. 4 being a perfect square, square root of 4 comes out to the answer of 2, and the square root of 2 just hangs along. So C is the answer of 2 times the square root of 2. So now you can see we had square root of 2 in both of them. The second triangle had a coefficient of 2. The first triangle technically has a coefficient of 1. And if you notice, those coefficients are the same values as the legs. So for this third example, it would be 3 square root of 2 for the hypotenuse. And the fourth example would be 4 square root of 2. So anytime you have a right isosceles triangle, the leg lengths will be identical, and those will be the coefficient for the hypotenuse value. And that coefficient is being multiplied by the square root of 2. So down on our generic formula here, if you have the leg lengths of L, the hypotenuse would be L times the square root of 2. Okay, now looking at this example here, we have the hypotenuse listed, but it is not a simplified radical. So first thing we want to do is simplify the radical of 200. And the perfect square number that goes into 200 would be 100, and 100 times 2 is 200. The square root of 100 is just 10, and then the square root of 2 just hangs along. So this square root of 200 is really 10 square root of 2 simplified. Now because we have it written in that formula, if I go back one stage here, the number in front of the square root of 2 is going to be the leg's length. So since this is a right isosceles triangle, the number in front of the radical is going to be equal to the length of the legs. So both legs are a length of 10. Now when we have a 30, 60, 90 triangle, it's a little bit different. Now on a 30, 60, 90 triangle, we are actually starting with an equilateral triangle. So if I was looking at this triangle in particular, and it had lengths of 1 all around, and I were to cut it in half, the base down here would now be 0.5. The hypotenuse would be 1, and you can see that it has doubled in size. So with this base length of 1, the hypotenuse would be double that, which would be a 2. With a base length of 2 here, the hypotenuse would be doubled. That would be a length of 4. Now this only works for 30, 60, 90 triangles. So it has to be the 30 degrees across from the shorter side, the hypotenuse is across from the 90, and the 60 degrees is across from the other leg. So if I continue the hypotenuse, it's just double the short leg side, and that's always across from the 30. 3 doubled is 6, and 4 doubled is 8. Now when we go to find the other leg length, we will be doing the Pythagorean theorem again. So we have our A, B, and C sides. So I'm going to do the Pythagorean theorem and then simplify. A squared plus b squared equals c squared. 1 squared is 1, 2 squared is 4, and I'm going to do a t-chart to solve. Subtract 1 from both sides. And to get rid of that squared, we are going to apply the square root. Now, because 3 is not a perfect square, I'm going to leave it as the square root of 3. That cannot be simplified using perfect squares, so the leg length is square root of 3 on that example. I'll repeat the pattern here, and then we'll see how this works for every 30, 60, 90 triangle. So I have my A, B, and C sides. So A squared plus B squared equals C squared. And again, apply that square root. Now with 12 is not a perfect square, but it can be broken down. So square root of 4 times the square root of 3 equals the square root of 12. Now because 4 is a perfect square, that just results in the answer 2. Square root of 3 just trails along. So b is the value of 2 square root of 3. Now notice the coefficient in front of that square root of 3 is the value 2, which is the short side's length. The coefficient here, which isn't shown but is truly at number 1, that is the short side's length here as well. So if I were to repeat this pattern, I just take the shorter side length and put it next to the square root of 3, and that is the longer leg length, the one that's across from the 60 degrees. So across from the 30 again, this is the short length, that'll be the coefficient, and then it's always square root of 3 by how it simplifies out. So if we're looking at the generic formula for this, whenever you have a 30, 60, 90 triangle, across from the 30 is our short side. If you double that, you'll get the hypotenuse. And if you take it times the square root of 3, you'll get the longer leg length. And that is lesson 9.3.